All right, here we are, chapter 10. Only two sections, but both a little lengthy because what we're doing in chapter 10 is we're taking chapter 8 and chapter 9, mashing them together and seeing what would happen if instead of looking at one population or group at a time, this whole chapter just does the same exact stuff, but when you're looking at two groups slash populations at a time. Section 1 deals with the proportions. Section 2 deals with the means. Today, we talk about the proportions. So, suppose we want to compare the proportion of individuals with a certain characteristic in population 1 and population 2. First time ever, two populations. Let's call these parameters. Now we have different, we can't just say P for parameter. We have to have one for population 1 and parameter for population 2. The ideal strategy is to take separate random sample from each population and compare the sample proportions with that characteristic. What if we want to compare the effectiveness of treatment 1 and treatment 2 in a completely randomized experiment? This time, the parameters P1 and P2 that we want to compare are the true proportions of successful outcomes for each treatment. We use the proportions of successes in the two treatment groups to make comparison. So, moral of this slide, very wordy, but the idea here is two populations now. Maybe we're looking at an SRS from each population in the top paragraph. Maybe we're looking at two treatment groups as different populations in an experiment. So we can do this with samples or experiments, but you can see here two populations. So we have parameters P1 and P2, which means we have statistics P hat 1 and P hat 2, and sample sizes N1 and N2 that definitely don't need to be the same. Okay, to explore the sampling distribution of the difference between two proportions, let's start with two populations, having known proportion of successes, let's say. We'll have two schools being our two populations. 70% of students did their homework last night at school 1. 50% of students did their homework last night at school 2. Suppose the counselor at school 1 had an SRS of 100. The school 2 had an SRS of 200. So we're looking at two populations, two separate samples. Okay. What can we say about the difference P1 minus P2? That's what we're going to do a lot of. We're looking for differences, right? If you're going to do a two proportion Z test, which is coming our way, or a two proportion Z interval, it's going to be on the difference in two groups. So let's explore. So using statistical software, we generated an SRS of 100 students from school 1 and a separate SRS of students from school 2. The difference in sample proportion was calculated at the end. So let's see what we did. Well, we know how we can find our P1 as 0.7 of this distribution, and we use square root of P times 1 minus P over N. We did the same with this one, and then we did their subtraction. One thing to note, remember, is that means always subtract. So to get this center of the new distribution of their differences, I was able to do 70 minus 50 and get 20. What I hope you remember is that standard deviations never subtract. Standard deviations also never add. What does add? Variances add. So we're going to have to look into how we get this 0.058. But again, if you remember that variances always add, you're well underway. So here it is. Here's the reminder. In chapter 6, we learned that if you want to subtract two means, just subtract them. If you want to subtract two random variables, unfortunately, the variation or variances or standard deviations will always get bigger. And the way to properly do that is to add the variances together, and then we'll take the square root. So, our shape. Look at what we have to do in order to check shape. We have to check n times p, n times 1 minus p. which was our original way, but now we have to do that for population 1 with P1 and then population 2 with P2. So we have to check 4 things at least greater than 10 in order to check for our approximately normal. We will get to those conditions in a second. The center is, of course, just subtracting, and then our new standard deviation will be to take the variance of the first distribution, P1 times that 1 minus P1 over n, add it to the variance of the second one, and square root the final variance to get the standard deviation. And then this says, if you are indeed sampling, meaning not experiment, make sure the 10% condition is still satisfied for each population. Here's what it looks like on paper. The center will be the difference of the p-hats. That will be our unbiased estimator of the mean, P1 minus P2. It will make an approximately normal distribution if the conditions are met. And then the standard deviation will be the square root of the individual variances added. Here we go. We saw this. So now we're using the same high schools, the same homeworks. In high school 1, we had a sample size of 100 and a sample p-hat of 70. So I check N1, P1, 70. N1, 1 minus P1, 30. N2, P2, 200 times 0.5. And N2 times 1 minus P2. And they are all at least 10. So we have to check all 4. What you're going to notice in this chapter is basically a double down on everything. Anything you had to check once in chapter 8 or 9, you just have to check twice in chapter 10. The mean was 0.2, and we see here that using the adding and the variances, that is indeed how we got the 0.058. And we have created a sampling distribution of differences. Why did we have to create that? Because without creating a normal curve for the differences, we never would have been able to continue now to do a confidence interval. Reminder that a confidence interval is still a statistic, plus minus critical value times standard deviation. These are still proportions, so our critical value will be on the z curve, but it will be a confidence interval for the difference of the two. 10% condition needs to be met when we are sampling. We will use this as our standard deviation. We will use z star for any given confidence level. So we still can do inverse norm for, we could do it for 5%, 2.5%, 1%, whatever it is you want to do, an inverse norm. You can, in order to get our z star. Same game. Now take a look. Here they are. Confidence intervals. So this should be reminding your brain of Chapter 8, Section 2. In Chapter 8, Section 2, we had to check that the data came from a random sample or a randomized experiment. Like I said, double down here. Check it twice. In Chapter 10, the data have to come from 2 independent random samples or 2 groups of a randomized experiment. 10%. If sampling, sample size 1 needs to be at least, population size need to be at least 10 times larger than sample 1. Population 2 needs to be at least 10 times larger than sample 2. So yes, chapter 10 is more writing of chapter 8 so far. All 4 of these need to be shown and checked using your p-hats. At least 10. So, since we don't know our P1 and P2, obviously, we replace those in our standard deviation formula, just like we did in Chapter 8. And here it is. Here is our confidence interval for the difference of 2 populations. So, the first thing is your point estimate is to subtract the 2 p-hats. Your z-star is found on the normal curve. And then your standard deviation is found using p-hat 1 and p-hat 2 and sample size 1 and sample size 2. Looks almost identical with a double down, remembering that point estimates can subtract, but variances always add. And let's take a look. We will also introduce the calculator now. As part of the Pew Internet and American Life Project, researchers conducted 2 surveys in 2012. The first survey asked a random sample of 799 US teens about their use of social media. A second asked 2253 US adults. We had 80% of teens use the internet and 69% of adults use social networking sites. All right. Obviously, these numbers have seriously changed, but we will press on. The first one is it wants to just make sure, can you calculate the standard error of the sampling distribution of teens minus adults? So the calculator is going to do this for us, but if you're straight up asked, you do want to know what you're doing. So let's see how all the pieces fall into place. The sample proportion of teens or adults, so I had 0.8 for P1, we had 0.69 for P2, and we have our sample sizes of 799 and 2253. The idea here is when you plug in your 0.8, 1 minus 0.8 over 799, add it to 0.69, 0.31 over 2253, add them and take the square root. So, an interpretation of standard error. Again, standard error is always typical variation in something in the long run. It's in the long run, the typical variation. So for this, it would be if we take many random samples, that's the in the long run part, of the same size, the difference in the sample proportion of teens and adults who use social networking sites would typically be, right, typical variation, about 0.0172 from the true difference in proportion of all teens and adults. So what this is saying is a 2 proportion standard error is if you take many samples of the same size, it's the typical variation of the difference, of the true difference. Typical variation of the true difference, because that's what we're doing. We're finding a confidence interval of differences, meaning how much difference there is from one population to the next. So very much the same. Standard error is still in the long run typical variation, and this time it's just in the difference from one population to the other. Question 2. Construct and interpret a 95% confidence interval and the difference between the proportion of US teens and adults. Well, this slide, we need kind of all of it. There's nothing that's excess on this slide, unfortunately. So start taking a look at exactly how you would state and plan for one of these. State. If you're going to use variables, you always identify them. Our parameter of interest, P1, the proportion of all US teens who use social networking. P2, the proportion of all US adults who use social networking. We want to estimate the difference, P1 minus P2, at 95% confidence. We should use a 2. Now, we like to say, this is a long name. We like to say 2 proportion Z interval, because there's no reason to put it over here if you could just plop it in there. 2 proportion Z interval. Random. The data come from 2 independent random samples of teens and adults. 10%, check them both. There are at least 7,990 US teens and at least 22,530 US adults. Needed 10% because this is sampling. Now look at the large counts. You do indeed have to show this. You do have to show me N1 P hat 1. You don't have to show this step, but you have to show the answer right here, 639. You do want to round these to whole numbers. I will show you more that you do want to indeed round these to whole numbers. Always, because that's what they stand for. So, and you show me N1, 1 minus P1. Show me that that is 160. N2, P hat 2. Tell me that. And N2, 1 minus P hat 2. Tell me that. Note the observed counts have to be whole numbers. Because all 4 at least 10, the condition is met. If something doesn't make sense to be a decimal, you don't make it a decimal. Right? If something relates to whole peoples. The do step. for chapter 10 is extremely long and time consuming unless you want to just use the 2 prop z int on the calculator. If you want to use the 2 prop z int on the calculator, you are absolutely in luck. You don't need to show any of that work. None of that needs to be shown. What we need is the answer to the do step is the confidence interval. Well, let me show you how to do it. Let me take a break from the slides, pull up the calculator. Stat tests 2 prop z int. Boom, right there. Now, I put in this data, but let me remind you. It said 80% of 799. 80% of 799 is 639.2. I did not include the 0.2. The calculator would give you an error if you put a decimal in any one of these. You cannot use decimals in any one of these at all. So round. This one was not 1555. I rounded it to 1555. Yes, close enough. Just use regular rounding rules. You calculate. You can see here that it gives you beautiful. It gives you your p hat 1. It gives you your p hat 2. You can see this is 80 and this is 69, just like I said, close enough. But what is the answer? Here is our confidence interval. Copy that directly to your paper. That is your confidence interval. And then just be very ready to interpret it. Let's interpret it together. Think chapter 8 here. We are 95% confident that the interval from 0.07588 to 0.14324 captures the, and now this is true difference, because we're looking at a difference in 2 proportion. True difference in the proportion of U.S. teens and adults who use social networking sites. You are going to have to practice this more, but indeed definitely rely on your 2 prop z int. And remember that you do have to check a lot of conditions and it will take you a little bit of time. Other part of section 1 is now the significance test. Here's the chapter 9 version for P1 minus P2. So, an observed difference between 2 sample proportions can reflect an actual difference in the parameters. Or it may just be due to chance variation, just like when we did a 1 prop z int. So what we're going to do is we're going to make our null hypothesis. You can write it 2 ways. I think the most popular is actually that they're equal, because you say the difference is 0 or the 2 proportions are equal. Remember, if you use letters, you must identify them. You can write these with no letters at all. You can write them with no letters at all, but if you use letters, definitely write them. Now, so our null hypothesis, we were going to restrict ourselves to a null hypothesis. The difference is always 0. So your null hypothesis, great, always looks like this or this. P1 minus P2 equals 0 or P1 equals P2. Whatever way you write the null, you write the alternatively the similar, like P1 minus P2 greater than 0, P1 minus P2 less than 0, or P1 minus P2 not equal to 0. The alternative is, if you wrote it like this, when I'm circling, just change the symbol between them. Just change this to less than, greater than, or not equals to, so it stays consistent. Let's see. How does this relate to chapter 9? In chapter 9, section 2, the data had to come from a random sample or randomized experiment. Here we have to check it. Double down twice, 2 random samples or 2 experimental groups. 10% if you are sampling, not an experiment. Check the populations are both bigger than their samples. Here we are. The counts of successes and failure in each group, N1, P1, N1 minus P1, blah, 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 at least 10. That's great. Nothing's changed from what I just showed you this slide about 10 minutes ago. Our z-score is going to be statistic minus parameter over standard. The statistic is the difference in the 2 p-hats. The parameter is our null hypothesis. It is 0 and not. Okay, so remember now, this is where it gets a little interesting. Just like in section 2, we used p sub 0 to check things. When we calculate our standard deviation, we do want to use a combined p, because if the null hypothesis is indeed true, then what we should be using is a p hat combined, where we add the numerators of p1 and p2 and the sample sizes n1 and n2 to get a combined total p. Let me show you. Take a look. Basically what it's saying is, just for a hypothesis test, and a hypothesis test alone but is the only one where you have a null hypothesis of innocent until proven guilty, meaning you have to assume it's true. Look how this just changed. From the confidence interval, we have no such thing as combined. Doesn't exist. With the hypothesis test, you want to use this p hat c for all 4 of these spots. I will show you the difference at the end, but remember, for hypothesis test, combined p hat. Okay. All right. So we still have a greater than 0, one-sided tail, less than 0, or not equal 0. Both the same. Still the same big, nasty looking z-score. Again, the calculator will help. Let's take a look at an example. Researchers designed a survey to compare the proportions of children who came to school without eating breakfast in 2 low-income communities. Population 1 had 80. 19 did not eat breakfast, so our p hat 1 is 19 out of 80. Let me write that down. 19 out of 80. Our p hat 2, school 2, SRS of 150. 26 had not eaten breakfast. Beautiful. More than 1,500 students attend each school. Well, we needed to know that so that we could pass the 10% condition. Do the data give convincing evidence at 0.05 level of a difference in the population proportions? Difference is keyword. Difference is keyword for not equals to. Difference in the 2 is keyword for not equals to. So let's take a look. State our hypotheses. We can say P1 equals P2 or P1 minus P2 equals 0. Both are acceptable. P1 minus P2 not equal to 0 or P1 not equal to P2. That's what the question wanted. We're going with not equal. We used variables, so we have to identify them. It's always a true proportion of something. P1 is the true proportion of students at school 1 who did not eat breakfast. P2 is the true proportion of students at school 2 who did not eat breakfast. If conditions are met, we're going to use, now again, 2 proportion z-test. Much easier. Keep the trend of 4. We've been using the trend of 4. Keep the trend of 4. 2 proportion z-test. 2 proportion z-test. Random. The data were produced using 2 independent random samples from school 1 and school 2. 10% is met for both. You have to check that for both. There are at least 800 students in school 1 and at least 1,500 students in school 2. It said it in the question. We're checking conditions with N1 and P1 hat. All of these, 19, you have to show that. You have to show 61. You have to show the 26. You have to show the 124. This line where I'm circling is you have to show that exact line. That is about as small as it gets. And then you tell me there are at least 4, so we have our large counts condition. This slide, essentially nothing can be missed. The only change I could possibly see is writing 2 proportion z-test. Now the do step. Let's take a look at some of this, but remember, you're going to let the calculator do this for you. P1 is the 19 out of 80. P2 is the 26 out of 150. P combined, just for hypothesis tests, is to do 19 plus 26 80 plus 150. 45 out of 230 is what you're going to use for p hat combined. Look at this at the test statistic uses the difference in the two, P1 minus P2, but then uses this P combined for all four places in the standard error formula. Your calculator will do that automatically. It's wonderful. Your calculator will do it automatically, and I'm going to stop and show you how. Stat, calc, to stat test, to prop z test. My numerator was 19. My denominator was 80. My numerator was 26. My denominator was 150. This was not equals to. And I calculate. You can see it gives you a lot. It gives you the z-score of 1.168. It gives you the p-value of 0.24, very high. And you see that the calculator in the background did your p combined for you. It's so lovely. It does the p hat combined for you. We don't, it's great to write all this out. But again, the most important things are z equals p equals. Obviously, this p-value is awful. We are going to fail to reject. Because our p-value of 0.2427 is greater than alpha of 0.05, we fail to reject H0. There is not convincing evidence that the true proportion of students at the two schools who did not eat breakfast are different. That was the word they used. That's the word we use. And that's the two proportion z-test. So I close with this. This is just to show you again that when we do the standard error for a hypothesis test, we have to use the combined p-hat. When we do the standard error for a confidence interval, there is no combined anything. It doesn't exist. So we use p-hat 1 and we use p-hat 2 to get our standard error. Okay? This is a closing slide on inference for experiments. One of the biggest things to remember is your notation. Talk about experimental subjects. Talk about treatment groups. Don't call them samples. And then don't check the 10% condition if things are experiments. So it is, most experiments on people are recruited volunteers. That's why we can't do 10%. That's why we can't say it's random. When subjects are not randomly selected, we don't generalize to the larger population. We still conclude the same way. Okay, we conclude our sentences the same way, but remember, cause and effect come from experiments. Conclusions about the broader population come from samples. Okay? This last bullet point really never happens. It says unless experimental units are randomly selected, don't check 10%. Yeah, there really aren't. Experimental units are not going to be randomly selected. That's it for section 1, chapter 10. Sorry it was long.